right, so I guess quick show of hands. Does anybody use GitHub Actions at work? Sweet. All right, cool. I hope I have something valuable for you. First of all, my name is Craig Wright. I am a Adversary Simulation Consultant at SpecterOps, which means that basically I get paid to break into systems, perform red team operations, and penetration tests. In my spare time, I pretend to be a professional chef, although my partner tends to think I just make a big mess. So quick agenda. We're going to be going over a sort of very brief introduction to what CI/CD systems are, and then we're going to go into the ways that they can be attacked. We'll follow that up with a deep dive sort of into GitHub Actions. And after that, we will do some demos. I did all of the things this morning. The demos should go smoothly, but if not, I've prepared some videos. And then some defensive strategies and options for people to hopefully protect these systems. So what is a CI/CD pipeline? This is going to be a set of systems which enable a sort of repeated and an automated way to analyze, test, and integrate your code, build it, and deliver it somewhere. That's kind of like whatever annoying definition, but I have harnessed the power of AI to create a diagram. And as we can see, this is like complete nonsense, and so AI doesn't know what it is. A lot of us don't know what it is, and so these are definitely places to try and understand in more depth. So what is it? So first up, we have the version control system. This is going to be something like GitHub or GitLab or Bitbucket. This is the place where you're going to have your actual source code stored. This is going to generally be Git-backed and provide some nice features such as branching, and we can track changes and see who's done what and verify that the actual people pushing code are who they say they are. Then there are the continuous integration systems and the deployment pipeline systems. We have Circle CI, Jenkins, TeamCity. There's probably more. This is a very interesting place to be, because a lot of these systems generally are going to have a lot of credentials on them for potentially very, very sensitive systems that they can access. And then finally, we have the artifact repository. This could be something like GitHub as well, or this could be S3 or JFrog Artifactory, where you're actually storing the compiled and built code out in a location so it can be accessed by other systems. In order to talk about attacking CI/CD, we are going to talk about a few things here. We're going to talk about the attack surface. So what is the actual attack surface for CI/CD systems? My favorite, or one of my favorite, is the developer's workstation. This is a wonderful place to live. Developers have access to many systems sometimes that they don't actually need. They also oftentimes do not have the best hygiene, and there can be credentials just laying around. And then this is also a potential entry point into the CI/CD system. Then we have the repositories. This is going to be either the local one on the developer's workstation or the repository that's actually stored up in your source control, such as GitHub. And finally, or not finally, but third-party dependencies. These are one of the more scary. This is one of the more scary components of the attack surface here, because you don't always, I mean, who's actually verifying that the compiled stuff that they're using for their builds is actually not malicious? So this is a very scary place to be. We'll have some examples to talk about this. And then build systems. As I said, this is a really interesting place to be for an attacker. If we can get onto that build system, we can potentially modify source code as it's flying through. We can also maybe steal secrets. There's oftentimes secrets for deploying things, or if we're talking about an infrastructure as code situation, there may be credentials for AWS or Azure in there. And then the artifact storage. Just, I don't know, 2 or 3 weeks ago, we found credentials in someone's bash history for Artifactory. We were able to upload a updated version of a package into Artifactory, and then the client later told us that this was pulled down into 2 additional stacks, which is a scary thing to think about because this sort of sidesteps a lot of the protections that can be laid in place ahead of time. So here's a nice little diagram. As I mentioned, we have the developer. This is a wonderful place to be for us. The developer generally is going to be pushing code into the repository. The repository is going to have some sort of trigger or configuration file which tells a build system or a runner how it should interact with the source code. And then the runner is either going to push this out to artifact storage, and then we have the consumer who is either going to pull the code from the repository or from the artifact storage. And as an attacker, we can enter pretty much anywhere in this whole path here. So the main places we're going to be talking about are the repository and the build system section. We will touch briefly on artifacts, but yeah. So a couple of real-world examples. So the first one, I'm sure everyone is probably tired of hearing about SolarWinds. I think that this is a work of art. This is really, really impressive stuff. The actual malware consisted of 2 components. There was the Sunspot malware, which was the sort of first stage, and this ran on the actual build system. Now, what it did is it ran as a scheduled task, and it would monitor for any new instances of the msbuild.exe process. And if you're not familiar with msbuild, this is the program that is used for compiling source code on Windows systems. So this scheduled task, it would monitor for instances of msbuild, and then it would grab the command line arguments and determine if this specific build was building something for a specific product that SolarWinds makes. It's called Orion. And if it matched that criteria, it would modify a C# file, and this would be compiled into a DLL. The second part was the Sunburst, and this is the actual malicious code that existed inside of the Orion DLL, the backdoor DLL. Now, the threat actors here were quite smart. They intended to sort of blend in with the expected traffic from Orion. And so, like, if you're familiar with Cobalt Strike Malleable C2 profiles, how you can modify what your egress traffic is looking like, this is essentially what they did here with their custom C2. And then this is commonly thought to be probably APT29, aka Russia or Cozy Bear. But the interesting part here is they were first in around September in 2019, and they weren't actually notified by a third party until December of 2020. Now, that's a pretty long time to be in there, and it's quite scary to think about this could happen. And so, looking quickly at the public repositories for SolarWinds, we can see that they are making use of 2 different CI systems. So we have Circle CI on the bottom, and then on the top, we see 124 instances of matches for a YAML file inside of a folder .github/workflows. And people who are familiar with GitHub Actions, this is going to be a workflow containing whatever build based on event. Our next one is going to be XZ. Now this got a CVE, and this doesn't really fit the standard CVE sort of definition, in my opinion, because this is just like backdoored code. But a helpful dev PRs a null check. If we look back at the history of what this Geotan user did on GitHub, the very first thing that they did was they checked, is this pointer, they made a pull request and said, hey, this pointer, we're not checking to see if it's null. And so they added just a simple null check, it got merged in, and then slowly over time, this user build rapport, and they're able to eventually become good friends with the original developer and gain more trust, and their code is getting merged in a lot quicker. Now, one thing that's kind of interesting about CI/CD systems is we have the ability to run like tests on our code. Now, for XZ, this is a archiving utility, and it makes sense that testing an archive utility, you probably want to be verifying that it is able to actually decompress files, and you want to give it broken files that are compressed and decrypt those. Now, there's some wonderful trolling if we go and look at the actual, when the actual malware is injected. Stuxnet levels of subtle. But here is the binary files that Giatan had added. One of these contains a binary stream, which is actually an encrypted payload. And so the full process here is that we have a malicious build script, which does some regular expression searching, and if you look at what it's actually going to find inside of the code, it's going to find one of these compressed files, it's going to pull out the encrypted blob, and then it's going to place it in, it's an object file, and it'll be compiled into the actual resulting XZ binary. And if we look here, we can see that XZ is actually also using GitHub Actions. And this is quite interesting. And so we can look back and see when did GitHub Actions actually get introduced? Giatan, thank you for your wonderful commit here where you're creating the initial version of the CI/CD workflow. So quick terminology, we have GitHub Actions. I feel like they did a interesting job picking these names. They all sound almost like they mean the same thing if you look at them from a distance. But we have GitHub Actions, and this is the actual CI/CD platform. And then we have workflows. Now these are going to be the YAML configuration files, which are used to define what actions are taken in certain events. And events are going to be the activity which triggers a workflow. So we'll talk about this a little bit more, but this can be things like issues or pull requests. We also have jobs. Now, this is going to be a set of steps, and the steps are the things that are actually performing something. Now, this could be a shell script, or this can be an action. An action is actually a separate repository containing code which should execute in a sort of repeatable way. So these are meant to like help developers throughout the process. One of the classic actions that you'll see is actions checkout, and then this one's just going to pull the actual code from the repository, and so you can work with it inside of the runner. The runner is the actual server or container which performs the building steps. Now this could be, as I mentioned, this could be, this is doing modifications to cloud infrastructure or compiling a binary or something like that. So workflows, here's an example workflow. This is a YAML workflow for, the name here is PR Slack notification. If you want to know if a repository is using GitHub Actions, you'll look for this folder, GitHub workflows. This will be at the root of the repository. And these are going to be triggered by an event or on a schedule. I guess you could say a schedule is an event, but, and then the other thing to note is that repositories can actually have like many of these. And so when you're looking at these to try and understand how they all relate to each other can sometimes be challenging because there's dependencies on each other. And so we need to go and look through all of this. So events, as I mentioned, this can happen on a schedule. This can happen whenever you push a release or make a pull request. In this case here, we have the trigger or the event for this workflow is going to be whenever a pull request is opened or synchronized. And in this example workflow, we also have our jobs down here, and this is going to be a set of steps. And we can see that this job right here is named notify, and we can see that this is going to run on the latest Ubuntu machine that GitHub is providing. This is a GitHub hosted runner. And then we have the steps, and these can be a shell script or these can be an action. I think we're talking about actions on this next slide. So we can see here, actions are going to be the application that's actually used in the workflow. And in this case, we're actually pulling a action from Slack API / Slack GitHub action. And we can see that it takes two parameters. The first is a message, and the second is the webhook. If we want to go check out what the actual code for this action does, we can take that string /API/GitHub action, and we can just append that to github.com. And we can see that this one is used to send data to Slack using a GitHub action. And so if we look in here a little bit deeper, we can see that the action.yaml file, this is where you're going to actually provide a sort of definition for people who want to use your action on what parameters are required, what parameters are possible, and so forth. So runners. I am going to reiterate this several times because I think that this is a super crazy and dangerous thing, but GitHub all over the place recommends that you never use a self-hosted runner for a public repository. They should only be used on private repositories. And we'll talk about that a little bit more when we go into the demo and actually prove how sketchy this is. So GitHub hosted runners, these are going to be free for a bit. You get a certain number of runner hours per month. After a while, you have to pay them. And I don't actually know what the cost is, so I'm not like in a giant organization where we're developing a bunch of stuff in these runners. So the thing about these GitHub hosted runners, which is really nice, is you have a build run and then they destroy it for you. They also manage and maintain this. You don't have to worry about secrets and stuff hanging around or bad builds leaving artifacts in a runner. You just have this thing run once and then it does what it's supposed to do and then leaves forever. With the self-hosted runners, however, these are going to be free for you to use. You just have to set it up, whatever the cost of your cloud infrastructure for running this thing, or whatever the resources internally you need to allocate to run one of these things. But these are going to be persistent hosts. The way that this runs is it's going to run as a shell script or a PowerShell script or a binary. These are available for OS X, Windows, and Mac. And these are going to be managed and maintained by you. But yeah, the big thing here, don't run these on a public repo. So, what kind of attacks do we have for GitHub Actions? The most obvious and probably easiest is probably stealing secrets. So we can look at any public repository, or if we've already breached the perimeter and we're internal and we're on a developer's workstation and we find a bunch of repositories, we can go looking for this sort of syntax here with this $ bracket bracket secrets dot. Now that's going to indicate that this repo or this organization has access to a secret which can be used inside of runners. Depending on what this is doing, this may be really valuable to attackers. And so these can be scoped to a repository or an organization, and they are going to be available regardless of any kind of branch protections you have in place. So I can just make a new pull request and grab this secret out of here. This isn't only going to work on main. And then GitHub does a pretty good job of trying to prevent this, but they're also like, if you do something crazy, you can expose your secrets in the logs. So when we're talking about actions and repositories and public repositories, we're going to be able to go to these public repositories and click the little actions button, and we can see the logs for everything that's ever run. And if something is done incorrectly, you can potentially have credentials sitting here. All right, so event context injection. This is whenever an event is triggered, there is a context associated with it, and this context contains values made to assist developers and make things easier. In this case, you can potentially have attacker-controlled data in one of these pieces of stored in one of these event contexts, and if the event context is taken and put in the wrong place, it can be executed. So in this example here, we have a variable title. This is taking the GitHub issue title, and this whole workflow here is meant to just check if the issue title begins with bug, because we're going to be mean to people and we're going to say, hey, you need to put bug at the beginning of your issue title. And then we take this next variable down here, content, comment, and we're going to pass that variable directly into there, and this is going to get executed. So the problem is that we can potentially inject commands if we make a goofy issue title. And we'll go over that in the demos. This is, again, when I mentioned don't run your self-hosted runners publicly, this is the reason. So you can basically inject your own workflows into someone else's runner. In GitHub, this is another quote from GitHub, forks of your public repository can potentially run dangerous code on your self-hosted runner by creating a pull request that executes code in a workflow. I'm not really sure why the default is set this way. It seems really dangerous. I'll show you how to fix it in a little bit, but this is totally crazy to me. But this is awesome for attackers. It's simple. We can just make a pull request, and we can fix something innocuous like a typo, and then have it merged into main, and now we are a contributor. And once we're a contributor, none of our following pull requests are actually going to be requiring approval. So if we make a workflow where the pull request, we make a workflow on a pull request event, and then we make a pull request, it's going to get executed. And it's not going to get executed on our runner, it's going to get executed on their runner. And we'll do that also in the demo. Now, another interesting attack is artifact poisoning. This could be poisoned in a bunch of different ways, and we're not going to actually cover this mostly because the implementation of this is going to vary really wildly. But to briefly talk about it, we have the third-party components themselves. If we go downstream somewhere, or I shouldn't say we because ethically this is not really something possible in most red teams, but a third party could have potential and malicious code injected into it, which you use, and then that gets pulled in and compiled with your stuff. We can also potentially modify the source code that is used on the runner. So the runner pulls down the code, we modify the code, and then that gets billed. We can also just replace the compiled code after it's been compiled. And then we can wait for something to push this up to the artifact storage. Now, this is a pretty interesting attack, and there's some pretty serious danger options here. So again, the problem here is that in one case, there's a great blog post here by Legit Security on artifacts poisoning, and this existed in the Rust-Lang. Now, what happened was they used that pull request trick that we just talked about, where a pull request is going to execute inside of a runner. Now, that runner is able to upload artifacts, and it does not upload artifacts on behalf of the user who made the pull request. It uploads artifacts on the repository. So when they pulled down, they made a fork of the GCC project, and they modified a workflow, and they added one thing in there to upload the artifact. It went into GitHub artifact storage. Now, what Rust-Lang was doing was they were pulling down the artifact from GitHub artifact storage, but GitHub artifact storage doesn't make a clear delineation between forked artifacts and the main branch or the base branch of the artifacts. So they pulled down a malicious version, and they used that in their workflow. Cache poisoning. This is a really, really cool idea, I think. You are probably going to break everything, but there's a really, really great blog post by Adnan Khan, who wrote all about a journey into looking into how to actually poison the cache. The long story short is, in my opinion, if you're able to get onto a runner, which is required to be able to poison the cache, there's probably an easier way to do what you're trying to do. So the idea is that you have this cache, which is scoped down to your repository, and that cache can be up to 10 gigabytes in size. And we are going to, if we need code for part of our compilation process, and we're using this GitHub action cache, we can store versions of the dependencies here, so we don't have to pull them a bunch of times and have all this bandwidth. So we can potentially inject code or inject into the cache, and we have to fill up and make sure we overwrite everything that already exists there. So that's one of the reasons why it's not really a super viable attack, because trying to upload 10 gigabytes of data, overwriting whatever's already in there, and still being able to put dependencies back there and not break everything, this makes it pretty challenging. And if you read this blog post, you'll find he had success, but he broke everything. So yeah, now we're going to do the demo. I have a virtual machine running here. We have, whenever you see this black background, that's going to be me acting as an attacker. This is my personal repository here, where we have a simple repo. And if we go into the workflows, the first thing I'm going to demo is the extracting secrets here. Now, the way that we're going to do this is kind of not exactly the best way, and I don't recommend anybody who's in the offensive world to do it exactly like this, but this is meant to illustrate the issue that we can sort of circumvent, which is they're not actually going to protect the secret here. So by simply taking this and piping this to base 64, piping this to base 64 again, we are going to evade their sort of attempt at hiding this. And so we can go ahead and commit this change. Commit straight into main, man. All right. If we go back over to our actions, we can see we have this workflow running. And if we wait for the action or the runner to initialize, then we have the output, and we can see we have base 64 encoded blob here. If we go ahead and, is that small? Is that better? Yeah. We can just, whoop, echo. I know how to type. Ooh, thank you. And we can see we have our Hacking in the Rain with Sasquatch here. So the thing I mentioned is that we should not actually do this on an operation because we risk exposing secrets like this. And also, it looks pretty sketchy. So probably you want to do something like maybe a curl request to an endpoint that you control and have the encrypted secret be sent out to there, but that's an exercise for you to handle there. The next one that I want to cover is the event injection. So if we go back to our workflow, we have our, 1 second, cancel this, stop running. Oh, I know, that's something else. Okay, so if we go back into our code here, we can look at this issue this check issue title workflow, and we can see that this is going to execute whenever an issue is opened or edited. We can also see that there are 2 secrets associated with it, and we have the permissions of the GitHub token here, which are scoped down as they should be to just issue Wright. And if we look here, we have that vulnerability that we were kind of looking at earlier, where we're going to have execution of whatever, potential execution of whatever gets put in here. So if we go into create an issue, we'll create a new issue. You can already see what I was doing before, but we can run like command substitution like this, ls-tech-la, I don't know, who am I? And then we can submit this issue. And if we wait a minute, we'll actually have the GitHub Actions bot respond with the output from this command. And there we have it. So the validation failed because, yeah, this is not what it's expecting. So we now have who am I, runner. We can see 2 files. We didn't pull anything down as part of our workflow, so there's nothing here. But Okay, so the next one I want to demo here is the actual malicious pull request. And so over here, we have a different user and this GitHub Actions BSidesPDX repository. Now, we can come in here and we can take this URL and we can go back over to our attacker machine. And we can be friendly and we can say, hey, you know, we're going to fork this and then we're going to fix something for you. So if we look here, we have now a forked repository, and we can go ahead and we can update this, this README here, and we can say, hey, you know, you forgot punctuation. Okay. Commit, and then we are going to go back to the root of our repository, and we are going to contribute. We're going to open a pull request, and we are going to say, yeah, you forgot punctuation. You need that. Create pull request. Now, over here, we are going to jump over to our other unsuspecting user here. They're going to take a look. They're going to see, hey, I got a pull request here. What is this? And they're going to do their due diligence. They're going to come in here, and they're going to see, okay, we have one commit. We have one file was changed, and this is simply adding a period. All right, looks good to me. Let's, all right, approve. Now, merge pull request, confirm, here we are. Okay, so if we come back, we can see now we have the merged pull request, and we can also see that, where is it? We have two contributors. One is me, and one is the original author. Now, if we come back over here, and we can make a new change, which is going to be, we're just going to simply add a new workflow here in the, we're not on the right branch, okay. Okay. If we come in here, we can come into the workflows, and we're going to add a new file. I'm going to do this all in the GUI. Okay, so we want to call this, I don't know, check-in.yaml. And if we have a previously built workflow here, which is also very, very small text, let's see. And so this is just simple YAML, and this is going to use a action that I created. And the reason I made this action is so that it looks a little bit less sketchy than straight up curling something and executing it. But this action basically just curls something and executes it, which is a good thing to know. So go away. Go away. 1 second. Here we go. Okay, so come over here. We're going to put our YAML here really quick. Let's take a look at the actual malicious action that I created. And if we go in here to source, we can see there's just one TypeScript file. This is not really doing much, but it's taking a URL and it's going to write it to this crazy path. And then it's going to run download, which is basically just an HTTPS GET. We're going to then run exec sync, which is going to change the file to be executable, and then execute it. So pretty simple, but we're relying on the fact that somebody's going to look at this and be like, I don't know what that is, or I'm going to have to go and take a look, and we can already delete the repo or something like that. So if we go ahead and we commit our changes here, we are going to run this, and then we will go ahead and contribute here. We're going to open a pull request to the original repository. We're going to go ahead and, yes, open, create pull. We want that. And if we wait for just a second, we can see now we are on the actual Snoitka users thing, and we can see that we have the YAML file executing. And if we go ahead and take a look here, we can see it's running git run. Now, if we go to our super awesome C2, BSidesPDX.org, C74443, we can go ahead and log in here, and we have a callback here from the repo, interact, and we're now running inside of this runner. And so we could run git env to access the credentials or whatever might be on this runner. And again, this is crazy because we don't have permission to run things. Why do we have permissions to run things inside of this? This is the default, so yeah, I don't know. Okay, so back to our presentation. Let's go. Defensive strategies. So first, don't run a runner on a public repository, a self-hosted runner on a public repository. This is that default configuration I was showing you, or I was talking about, where we require approval for first-time contributors. Only first-time contributors will require approval to run workflows. This is, in my opinion, an insecure default, and this should be changed. We should switch that over to this one, require approval for all outside contributors. Additional security for the actual runners, I would say that if you can minimize the actual access that it has to any other resources and minimize the actual outbound internet access it has to things, to only what it needs. That would be my recommendation for these. GitHub documentation is quite good. They do definitely a million times remind you, do not use a self-hosted runner on public repositories. And I'm not going to say anybody's name, but I looked around at a couple of organizations in Portland, and some people are doing this. So don't do that. Yes.
How does the adversary know when you're using a self-hosted runner?
It's in the YAML file. I can show you in a minute. We'll get there. Okay. So for repositories, I recommend using a code owners file, and this is going to be similar to a git ignore file, but this basically is saying this repository is owned by, or this folder or file is owned by a specific user. We can add specific folders into there which require approval, so even internal employees can't actually modify files in certain places. Then enable branch protection, which will get you commit signing. This is going to cause me a lot of problems as an adversary if I'm on a developer's workstation and I want to grab secrets. If you have commit signing enabled, I need to kind of wait until the actual developer comes and makes a legitimate push and doesn't notice that I have modified anything. So this would knock out a lot of that. For the actions, I don't know if you can see this, but this is a typo up here. It's ATCIONS. I created this the other day. It was pretty easy. It looks pretty legit too, I think. But use caution with your actions. Make sure that you're doing some amount of validation or vetting of like what it is that you're running. And then make sure that whenever you are going through to modify these things that you're always using the most up-to-date version. And then the secrets and the GitHub tokens. So this was a quick search that I did here. On the right in the bottom, we can see there are a bunch of secrets, and they are defined as vars. Now, if we look in the top right, we have secrets and variables. When you go to add these secrets to your repository, you can choose to add secrets or variables. It does not protect the variables in the same way that it protects the secrets. And so if something errors ever, any of these pretty juicy looking secrets could be exposed. And then, as always, limit the scope of the actual secret. Like, if you need AWS creds in a runner for some reason, you should just make sure that that can only do what it needs to do, and not admin ***. And that is, oh, acknowledgements. Yeah, so while I was doing a lot of this research and looking into this stuff, I kept coming across these two names, Adnan Khan and John Stowinski, so I definitely wanted to give them a huge shout out because a lot of whenever I was like, ooh, what is the attack surface here, I would end up on a blog post by one of these two individuals. If you are a developer and you are using GitHub Actions, there's a pretty cool tool that the two of them have worked on called Gato X, the Extreme Edition. I would definitely recommend that you do not do any of the sort of exploit attacks that are possible with it, but stick to, it has a sort of analysis you can scan for vulns. Yeah, I think that is all I have. Oh, I wanted to show you the self-hosted runner thing real quick. So if we go real quick to the, this is what you'll be looking for. This runs on. It'll say either Ubuntu latest or it'll say self-hosted. In this case, we know that this one is self-hosted. You can also go to the actual repository here. All right, is everything, okay. If we go into Actions, this is how you can see. You have that GitHub Workflows folder, and then we can see that my C2 agent is still running, which we can go ahead and kill. And yeah, so we can look in here, and we can see details about these merge requests. We can go ahead and view the specific action, and if this is a public repository, we can see all of this stuff as anybody. So we can come in here, and we can see okay, it's doing some setup here. We have the runner information. This is a different workflow, which is just made to show the repo that it's running as. But yeah, that would be how you look for it, is that self-hosted string in the yeah, the file. Yeah.
What's the GitHub signing with a hardware token support like on a Mac? Does it work?
Yeah. Yeah, I think there's a, so the slide, there's a link on the specific page where I talk about that. Why is this here? And this is a QR code to the slide deck, so all the links are on the bottom there. But yeah, so you can set up for YubiKey. I know that they just had a interesting fiasco. But YubiKey, you can get your YubiKey to sign your commits. So GitLab, I didn't actually focus on GitLab here, but yeah, there's a similar thing going on. I'm not sure with the pull request into the actual runner, if that works the same. It possibly does. I don't know. It'd be fun to test. Thank you, guys.